Well, good evening, everyone. Depending on the time of the day you are watching us from, so we want to commence this experiment tonight by want to study three-phase system. This experiment is a requirement for the course for 201, that is applied electricity. It's a 200 level course of the Department of Electrical or of the Faculty of Engineering, Nnamdi Azikiwe University, Awka. The experiment, and I know several universities across the nations and across the world run virtually with similar curriculum. So even if you are not a student of the faculty, you can still find this experiment very useful. Okay, so the three-phase system, due to the unavailability of the equipment in order to carry out this experiment, we have devised a software, that is LT-Spice, that we're going to use to run this experiment. Now in this experiment, it is important for us to know certain things: star connection, data connection. You know what star connection is as electrical engineering students, and what a data connected system is. A load could be connected in star or could be connected in delta. So I will quickly show us the diagram. This is a diagram for a star connection. When you look at this, each of the branch of the three phases are connected to a common point. The terminating end of each of the branches are connected together to form a neutral point, while the starting ends are connected to the supply. That is what gives us a star connected system. While in the case of a data connected system, each of the branches are joined in this manner. Okay, so the terminologies that we need to know are line voltage, line current, phase voltage, phase current. Line voltage is the voltage that exists between two lines. That is, in the case of star connection, now the voltage between this line, if this is red phase, this is blue phase, and white phase, that is the yellow phase. The voltage between red phase and yellow phase, that's RYB, is what we call the line voltage. The voltage between red phase and blue phase, RYB, the voltage VRB, VRA, VRC. So those are the line voltages. While the phase voltage is the voltage between a phase and the neutral, as can be shown on this diagram. So without making much ado, we want to connect a data connection and a star connection. Then we measure the voltage. Now this is the table of values. In this experiment, we want to run this experiment and see the line voltage, phase current, then the ratio of both. Then we will be able to calculate our power using the formula stated here. Okay, so without taking much of our time, let me quickly launch the LT-Spice simulation software. This is LT-Spice. So this load has been connected in a data connected system. Like in theory, you are told that each three-phase of an electrical system, of a three-phase system, are separated by 120 electrical degree. And that's why when you check what I've connected here, you see that I've picked a sine wave which represents our three-phase system, 0 volts as the DC offset. The amplitude, I've selected 212 volts for the amplitude. Where I got this 212 is in the manual, in the laboratory manual, we were told that the voltage, the line voltage, is to be given a value of 150 volts. That is, and you know, universally AC voltage and current are measured in RMS value. So if you are given an RMS value of 150, so definitely your amplitude is going to be 212. That is, VRMS is equal to amplitude voltage over root 2. That is, amplitude voltage now becomes root 2 multiplied by VRMS. So that is where we got this from. And the frequency, as usual, we know it to be what? 50 volts. So you do the same thing, and the phase angle is 0. For the second phase, we configure it to have a 120 degree electrical shift, because each of them is to be separated by 120 degree. And the third one is going to be 240 degree. That is 120 from each other. So having done that, let's quickly run this simulation. You run the simulation by going to this menu bar, click on this guy running. When you click on it, you want to see the voltage at each phase. The voltage at this phase, when you click on it, you get something like this. And you click on the second voltage, the second phase, you get something like this. And you click on the third phase, you get something like this. So when you look at this waveform you are seeing here, you will agree with me that this is a three-phase system. Check your textbooks, online sources, and all manner of places where discussions have been made about three-phase system. You will see the waveform being represented like this. So this is a three-phase system. So let's quickly verify something very important. We said they are separated by 120 electrical degree. Let's see whether these guys are actually separated by 120 electrical degree. So how you can do that is simply click on this to bring out this cursor. When you click on this to bring out this cursor, you can now we have clicked on the green, that is the voltage V003. Now let's click on red so that we can easily measure. We want to measure the phase that separated them. So this is the second, why this is the first. Let me see, this is the first. Let me make this one the first waveform. Then let me make the red the second waveform. Let me make it the second, so that we cannot have two different cursors. We want to measure the red, the peak of this red. Then you want to measure the peak of this red. This is 1 and this is 2. So we want to measure the peak of this, then the peak of the red, and the peak of this. So let's measure the peak of this. Each of them at their peak. Make sure you are using the very peak, the highest value you can get for this vertical axis. Let's make sure that it's the highest value you can get. So let's say 212 is supposed to be 211, 212. Can we get to 212? Okay, I think we can get to 12. 211.341 is what we get here. Let's see what we can get. 341 here too. Let's see what we can get here. 211. Let's see what 211.847. This one give us 847. Let's see whether this one can give us 847. 211.8. This one can give us 211. Okay, I think the highest we are getting here is 211.34. 211.34. I think let's just leave it here. So we have measured the two cursor points, the peak of this voltage, which is voltage green, then the voltage red. Let's say this is red, blue, and yellow. Let's this green represent the yellow color, or we can change the color if you like. Let's change it to color yellow. Let's change it to color yellow so that it will agree with red. This is red, blue, and yellow. So now you want to measure the phase angle quickly. So when you look at the two cursors, say cursor difference is 6.773 milliseconds. That's the difference between this point where you put this cursor and this cursor. And you know this is the peak of this is the peak of this phase. So there is a formula we are going to be using shortly. Let me bring out the formula. Now look at this place. To find the phase angle. Phase angle equals to 360 multiplied by TD over P over T, that is over capital T, which is the period, where TD equals to the period. So that is the formula we shall be using. So having understood this formula, let's quickly bring out our calculator and punch. Let me bring out my calculator from here. Take note of the formula. So 360 multiplied by what? By TD. The time difference is already 6.773. So if you convert that into milliseconds, you'll be getting something like 0.00. So 0.00673. Then our, like from the formula that I show on the board, from the formula, if you come here, from the formula you know our period t equals to 1 divided by frequency, and the frequency we have set, the frequency is what? Frequency equals to 50 Hz. So if the frequency is 50 Hz, that means 1 divided by 50 will give you 0.02 seconds. That is the period of that waveform. So we have to put that into the formula. So 0.00673 divided by 0.002, that one give us 0.33865. Then multiply by 360 as the formula indicated. Multiply by 360 give you 121.914. Now when you look at this, you will discover that it is very close to 120. The reason why we couldn't get 120 is might likely be due to the error, the human error that occurred in the process of trying to get our peak value, the peak point here. So that is where the error comes from. But in this sense, it is actually going to be 120 electrical degree. Having done that, let's quickly measure our voltage. Now, since we already know from what we see on the board that the three phases have the same value, so we can safely delete some of the two of this waveform, and we take measurement of one to get our phase voltage. So if you measure this to get the peak value, what is the value you get? You get 212.0871 volts. That is our phase voltage, the voltage in each of the phase. And you now use the formula √3 multiplied by V phase will give you V line. So you'll be able to feel that phase voltage. Then the phase current. If you want to measure the phase current, try to click on that simulation again, then probe inside the resistor. You get the phase current. Probe inside the resistor. What happens? It's like have I changed any value here? Arrow 100. Okay. Let me simulate this thing again. I want to get the current, and the current. So these are the three currents. So I want to get the current. So what we do is the same manner. You probe to get the value. You just need one. So let's delete the other. You just need one. Let me delete this one. You just need one current. So you click on this and you trace the peak value. The peak value gives us 6.33783 amps. That is our phase current, and it is the same thing as line current. Then the next thing in the experiment is to find the line voltage and phase voltage. Okay, then lastly we find the power by using power. W equals to √3. Power equals to what? √3. Power equals to √3 multiplied by cos theta. Now cos theta, we have gotten it to be what? Now cos theta. So how do we get our cos theta? Cos theta is simple. So let's go to how we can find the phase angle. The phase angle, cos theta is the phase angle between the voltage and current. So we need a voltage and a current. Let's say we have taken the current in this R1. Let me equally take the voltage so that we can find the phase angle. So if you find it, you can easily make use of this. So this is a resistive load. When you look at it, you discover that the voltage is falling on each other. The voltage is the one that is carrying a color blue, while the current is the one carrying a color green. The reason why I put this minus is to invert the phase, because LT spice, same with approaches used to invert current So you have to use that minus to return it back to the way it was supposed to be. Because if it had been the other way around, you know, this is a balanced load. There's no capacitor, there's no inductor, so there's no need for that phase reversal. So what will you do when you look at it? You find the phase angle that separates both, just the same way we find the phase angle the other one. You get the cursor of this, the cursor of that one, then you use the formula that we have said earlier on to find the phase angle. So that is that about the three-phase delta connection. In the next video, I'm going to be showing you how we run three-phase star connected load. That will be not all for now. Please kindly subscribe to this YouTube channel in order for you to get more videos as they will become available. I'll be putting them here so that once you run out, if you encounter any issues, you can easily revert to the video to watch and get yourself acquainted to how these simulations are run. Thank you very much for your time. My name is Engineer Clement, Department of Electrical Engineering, Nnamdi Azikiwe University, Awka, Anambra State. Please click the notification button and subscribe to this YouTube channel to support us. Thank you.